I'm very happy and really honored to introduce our next speaker, Professor Ivette Fuentes from University of Southampton and also from Oxford University. I think you could say that she's famous for bridging the gap between the abstract fundamental theories of quantum gravity and the practical experimental world of quantum information science. Is that correct?
I don't know.
and of course, she's actually here because she was the faculty opponent in the physics department yesterday, and hopefully that all went well. And of course, I don't know if any of you know, but I sometimes wonder how you manage to do everything you do, because you participate on all these great discussions all over the world, and also you have time to interact with Roger Penrose, and so. But anyway, so we're looking very much forward. And
thank you. Yes, I think I've been trying to do more than what I can chew. And I think now I'm going to slow down a little bit, a few months, because I overdid it. I don't recommend it. I mean, it's nice, but yeah, it's also not possible to be everywhere. If you're not quantum, of course. It's the second time I hear the word famous recently, but because I never use it, but I had to use it a little bit yesterday when I was coming in, because as I was coming in, they wouldn't, I mean, I don't know, I had to say I was an opponent, and they asked me, what's an opponent, what is a PhD, all kinds of questions, and then he asked me, how do they select the opponents? And I said, I don't know, I'm a famous physicist, I don't And then he let me in. But I would never, I mean, it was out of desperation, I guess. Anyways, so yes, I'm very interested in the interface of quantum mechanics and general relativity. And I think the way that I see things is that I don't, well, and this is coming out from my recent work, which is not finished yet, but what I'm learning from it, I think that we cannot resolve the problems of quantum mechanics by quantum mechanics alone. That's my opinion. We need to take gravity into account in order to resolve the problems of quantum mechanics. So there's this two different ways of doing it, and some people take the view that we first need to solve the problems of quantum mechanics before we can even think about how to unify it with gravity. But what I am finding is that we have to do it together. So I want to tell you about that. But well, there's many interesting, beautiful questions in fundamental physics that don't have answers so far. So what is the nature of dark matter? Is dark energy driving the accelerated expansion of the universe? What physics dominates the universe at early times? Does the equivalence principle hold for quantum systems? And I'm going to tell you something, a new experimental result that says something about this last question. But anyway, underpinning all these beautiful, interesting questions is our difficulty to understand and find answers to these questions is the fact that quantum mechanics and general relativity are incompatible. So when I was a student and I was learning physics, my teachers told me that quantum mechanics applies to the microscopic world, to the very small, where atoms and electrons live and short distances and few particles, and that general relativity applied to the big scales, starting maybe from Earth. With satellites, we already have to make corrections due to GR to have the accuracy that our phones have. But what I'm going to show you is that experiments today already show that this division is not true. And then it becomes very interesting to try to understand where does quantum mechanics start and where, I mean, this division is again pointing out that we need to look at things together, because I'm going to show you from the experiments how this division is no longer true. So I stole this slide for some more general public discussion. I was trying to explain the difference between quantum physics and classical physics. But when we learn quantum mechanics, the first thing we learn is well, if you do it with postulates, is that the state of a quantum system is a vector in the Hilbert space, and already taking the first step, we're in trouble because we don't know what is, we haven't reached an agreement yet. And to show you this, that this is the state of things at the moment, I don't know if you saw this article in Nature or if you participated even in the poll, but many of us were asked what is our favorite interpretation. And you can see still most people are voting for the Copenhagen interpretation, but with very little confidence. And well, I voted for other because I think I'm kind of going to come out soon, hopefully with my own work with more confidence. I hope, but this really shows how in 100 years we're still kind of very indeterminate, undecided. So I am a physicist that is interested in philosophical questions. In particular, at the moment, I'm very interested in what is mass and what is time. I'm a physicist that loves to talk to philosophers, so I'm doing that now more and more and more. Actually, now my son just started university a couple of weeks ago, and he studied philosophy, so I'm very jealous of him, to be honest. I wish I could swap with him at some point. But anyway, maybe one day I can discuss these things with him too. So it makes me think about, so that the foundations of modern science are grounded in the materialistic metaphysical position. All of the science that we do is based on the idea that what's fundamental are particles and fields. But when you think about a massive particle being in a superposition of two different positions, well, I mean, we don't only not understand what the wave function is, but we don't know what mass is. The other day, I told this to a colleague, and he replied to me, "That's nonsense." I said, "Okay, maybe like I'm missing something." But then I just realized that there are some physicists that they just don't like philosophical questions. And that's fine, because we need that kind of physicists to do some other things. But some others, like many of us here, we are interested in going sort of deeper into things and trying to understand them. Okay, this microphone is playing me tricks. And these things, no? So I was thinking, if particles are fundamental, or if mass is fundamental, and we have a superposition of two parts, do we have 2 times the mass? I don't think so, right? That doesn't make sense, because the particle can be in many places at the same time, so n times the mass. No, I mean, the notion of mass in quantum mechanics, if one thinks about it properly, doesn't really make a sense, or at least we don't know. And I'm afraid that we have taken the route of saying, shut up and calculate, or don't even really go into much of a discussion of this, or at least this is in my environment what has happened with this question. But I think really when you want to unify quantum mechanics and general relativity, you need to think about this question really, really seriously and deeply. And I like to think it's like, if our paradigm that mass is fundamental and mass is in a superposition of left and right, does this mean that our paradigm, our materialistic paradigm, is in a superposition of right and maybe wrong? I don't know. But I mean, I want to just, of course, I'm being provocative, but what I want to do is that I think that quantum mechanics, if you think deeply enough about it, challenges the very basics of what we see as reality and as our paradigm. Now, if you go into quantum field theory in Kerr space, that I started to study that some years ago, I mean, the first thing that you learn is that particles are ill-defined. If you have a curved background and you look at the particle content of the field, even inertial observers disagree on the vacuum and on the particle content of the field. So each inertial observer sees a different thing. So therefore, from there, when you bring together quantum mechanics and general relativity, as in quantum field theory in current spacetime, which is semi-classical, it's not the full theory yet. Already there, you get that particles are not fundamental. What's fundamental are fields. And what I'm finding from my current work is that even when you go to quantum mechanics, if you want to have a theory that sort of describes, I agree with what Chris was saying. In my theory, it has some flavor and some elements of what you're doing. I mean, about the bomb theory, in the sense that I'm also getting that the classical world is emergent. So in that, I completely agree. And actually, I have some functions, like the ones that you have, but they come from gravity. So maybe it would be nice at some point to talk about that. But what I'm finding is that you cannot have a particle description of physics, of quantum mechanics, not even with one particle. You need to go to fields. And my paper now, I've been saying it's going to come out soon, and it's been 3 years now. So I don't know, soon is relative, and whenever it's ready, it will be ready. But I'm starting to talk about at least some of the ideas that will come. And one of them will be that you cannot talk about quantum mechanics in this particle sense. It always has to be fields. And what I'm also finding is that the classical world is emerging from the quantum world. So how I take my perspective about quantum mechanics is similar to Roger's, similar in some aspects, different in others, but in which I agree with him is that I believe that there is a quantum reality. I believe that the quantum states really are talking about a physical reality, but we don't live in it. Right? And then there's the classical reality that is the emergent one, the one in which mass is understood in the classical way. So the notion that we have of mass is a good notion in the classical world, but in the quantum world, I'm going to propose a new notion of mass, which I think that is the ingredient that allows one to move forward. Okay. So let's go and talk a little bit about, because in my talk I promised to introduce some notions of relativity and how to put things together. So in quantum theory, time is absolute, so all clocks tick at the same rate. And space and time are very different notions, same as in classical physics and in our own experience. In the Schrödinger equation, time is a parameter, and we find one derivative, a first-order derivative in time, and then positions can be quantized. There's a second-order derivative for positions, and we use operators to describe positions, so very different also from the mathematical perspective. And then we get that particles can be in a superposition at two different locations at time, as I was just talking about. Now, if you move to relativity, time and length are observer dependent, and they're not different notions. They, in a way, belong together. That's like maybe the most radical thing that we learned from Einstein is the notion of a higher dimensional space that we call space-time. And then we get that if we have mass and that bends space-time, then we look at clocks at different places, and they will click at different rates. So if we have, let's say, the Earth, and then we have a superposition of a massive particle, time will click at different rates and different points, but we have the system in a superposition. We don't have a theory right now that can describe this very simple situation, no? Or at least not yet. So in my opinion, the most important question to look at is what happens with a massive system in superposition. There are people questioning if it makes sense to quantize gravity. I think that yes, that you have to. But a way that one could see it is you have a mass, and the mass curves the space. And then if you have a superposition of the mass in two different locations, would it be like having a superposition of two space-time configurations? So we know actually that you do. If you have an atom, we have atoms. Actually, I'm going to talk about how big can you have a system in the lab in a superposition. So you can have molecules. So if you have a molecule, it will be bending space-time, and you do have like a quantum gravity situation in this case. It's only that it's very, very small. And the question is not about do we have quantum gravity, but it's more about is it a stable situation? And I believe that it's not, and because of reasons very close to what Roger has proposed, that gravity is somehow the culprit in this transition between the classical world, the quantum world, and the classical world. So these questions about massive systems and superpositions help us think about if we should quantize gravity. So this is a question that Roger likes to pose. Should we quantize gravity? So what he means by that is keep the principles of quantum theory as the fundamental principles and modify general relativity in order to unify them. And he doesn't like that program because he thinks that quantum mechanics is wrong or has problems because of the measurement problem, because our difficulty finding what is the ontology of the wave function. And he prefers the idea of gravitizing quantum theory, in which he says that we should keep GR as a fundamental theory and modified quantum theory. I used to agree with him, but not anymore. I think that is a good thing when you're... I see Roger a bit like... I met Roger when I was already a full professor, but still I see myself as a student of him in a general way. So it's good to go against... students should be rebellious. So I am a bit rebellious in that sense, because what I am finding with my work is that GR is my work is going to be Newtonian at the moment. Then I'm going to work on the relativistic case. But already you can see what to expect. And I think that you should not be quantizing gravity in the sense that taking GR and then trying to quantize its elements. I think that GR is an emergent theory, that you get GR as in the classical world, from a more fundamental theory in which you actually have to modify both. You have to modify quantum theory, and you have to modify something that is gravitational, that once you take the transition, then you get GR. And this is very different to what people have been doing so far, but this is what I think one should be doing. Then there are other proposals, like Jonathan Oppenheim's, who's a university college. And I like one thing about work. I mean, I disagree with Jonathan because I think that gravity should be quantized. But what I like very much about his work is that he comes up with his model, with his proposal, and with an experiment together that can be sort of tested. And this is the sort of thing that I think we're ready to move into because of how quantum technologies have been developing. And I want to spend, like, this is sort of, I told you, like, my general ideas and the way I see things, but what I want to do in the rest of the talk is I want to tell you about experiments and how they're challenging some of the preconceptions that we had of the theories, and well, a little bit more about my work too. But I think that the thing that is important for me is that thanks to quantum technologies, we're ready to start guiding our theories with experiments. So I found this image in the internet. I think I showed it to you, some of you before, but I liked it very much because it made me think of humans like very romantically sitting in the fireplace and looking at the stars and trying to ask philosophical questions like, who are we? What are we doing here? What is this reality? And having as their only instruments their eyes, and how difficult it is to answer questions in, let's say, in physics by having your eyes as the only instrument. So Galileo took the telescope that already existed but wasn't used to point it out at the stars, so he did that. And very interestingly, many people didn't want to look through it. So I think this is like, oh, I don't want to think about what is mass, and I don't want to think about what really quantum mechanics is telling me, because it works and we can make lasers and we can make things. So I think that's a little bit similar. But anyway, since Galileo did that, well, the instruments have developed very, very much. And now we can see super far into the past of the universe. We can see that the universe is expanding and so on, and we can start making much better cosmological models. Also, if we think about the atom, the Greek first came up with the notion of the atom and took, I don't know, 2,000 years for us to develop the instruments. And then now we can look into the microscopic world and do very serious atomic physics. So that's the point I'm trying to make, is that when it comes to the scales where quantum mechanics and general relativity interface, we're blind. Like worse than like the caveman looking into the stars, because there's no instruments, nothing, completely blind. Or we were. I'm going to show you that this is not the case actually anymore. But this is the difficulty of trying to make theories when you have nothing to observe. And from a mathematical point of view, you can come up with so many different models, so many different theories. But what do you have in order to decide? Well, one are the philosophical standings, and the other one is the experiments. So what I am interested in producing, I mean, my work has been for many years in trying to focus on trying to build those technologies and those experiments that allow us to look into these scales where we've never looked into before, so that we can start doing some serious science there. But what I am really interested in sort of getting at is into putting the field in this cycle in which, okay, people like me come up with some models and maths, propose an experiment. The experiment is tested. The experiment would say yes, no, or some things that we maybe need to modify. And then enters philosophy and creativity, philosophy to interpret the results, or does the experiment is telling us something new about time, something new about mass, and so on. And when it comes to, again, this interface of quantum mechanics and general relativity, this cycle has been missing. So, but we have the tools now. And also, this is an important thing that I think that is a really good time that physicists start talking more to philosophers, so that we can do this together, because we have to do it together. Actually, it's quite funny because my son is handing in an essay today, his first assignment at university, which is about why his father and I are physicists, and it's like why physicists need philosophers. So I found this very, very telling. Okay, so let's start talking about experiments. And I first want to tell you about long range, because those experiments already reached relativistic scales. Then I want to focus on large mass and tell you some of the work with Roger that got my current work inspired, and a little bit about what I'm doing now. And then if I have time, I will go more into high sensitivity. So, well, this is how when I was a PhD student, how the experiments that Anton Seilinger and Eileen Aspect and John Clauser were doing to distribute entanglement between photons in the lab. So they started with tabletop experiments. And then, well, Anton started to do the experiments across 2 buildings in Vienna. Then in the Canary Islands, 2 different islands, 144 kilometers. And well, I mean, keep going. And then, well, Zhang Weipan used to be in his group and then moved to China. And they launched a Mesius satellite, which is exclusively purposed to do quantum experiments in space. And now they can distribute entanglement across thousands of kilometers. So you remember I was telling you about these scales that we were, when I was a student, says, oh, quantum mechanics applies to the small, and general relativity to the big. Well, now we have that quantum experiments have reached scales in which satellites already operate. And then I'm going to show you that the opposite has also happened, that we say, oh, quantum mechanics applies to the very small, but precisions of quantum systems is so much that you can actually see time dilation at almost reaching now millimeter scales. So this division is no longer the case, and I think that is also why I think that in order to really understand the theories, the only way to do it is from the beginning, putting them together. So yes, so I was saying that at the scales where satellites operate, relativity kicks in, and that is why our GPS has to make these corrections. But now if you have all these quantum experiments taking place between satellites, and we know the proper time on Earth is different from the proper time in satellites and so on, if you go on using just non-relativistic quantum mechanics, you're going to get things wrong. Okay, so what do experimentalists do? They know about the gravitational redshift, which is a special relativistic effect, and they make corrections about that. But we don't have special relativity, we have general relativity because the space-time of the Earth is curved. So this is how my work, one part of my work started many years ago. I used quantum field theory in curved space-time to describe these experiments. So we modeled the space-time of the Earth using a Schwarzschild metric, which is not a bad approximation. And then we considered the wave packets that Anton prepares as wave packets using the solutions of the Klein-Gordon equation in that metric. We started with simple 1+1 dimensions and simple things to start with. And then we studied how the wave packets were deformed by the curvature of space. And we found that they don't only get redshifted like the special relativistic effect would show, but because of the curvature itself of the Earth, the wave packets get all deformed and flattened and so on. And then we showed how this would affect quantum teleportation, quantum cryptography, and then we turned things around and we used it, I skipped that slide, to using quantum metrology to measure space-time parameters using those techniques. So my background, how I got started with quantum information and quantum metrology, and then I slowly moved into being interested in the interface. So then those, let's say that background allowed me to look at things like that, and I have a lot of interaction with the space-based experimentalists, and hopefully not in the too long, they will start testing some of these predictions. I was in a conference in Glasgow recently, and they're getting there slowly. Now I want to jump to big mass. Can somebody tell me when I have, I don't know, 10 minutes or something?
I will tell you when you have 20 minutes. You have still plenty of time. You have half an hour.
Oh, perfect. Yeah, because I have loads of things to talk about. Yeah, no, I have a lot of things to talk about. It's just like I usually spend too much time at the beginning. Okay, so this is where things are at in the lab. Markus Arndt at the University of Vienna has the record in putting a particle, the biggest particle in a superposition. So he has molecules, I think it's keratin, and they have 2,000 atoms. This is what I last saw in the literature, but I met Markus not that long ago, and he told me that apparently they have one order of magnitude more than that. And he can keep the superpositions like for milliseconds, something like that. Then comes, would say, Markus Aspenmeier, also at the University of Vienna. So also Anton is there in Vienna. So Vienna is an amazing place for doing quantum experiments. I actually, because of that, spent 3 years as a visiting professor.
Is that spatial superposition or state superposition?
This one is this experiment here is a spatial superposition. Okay, so then this thing here for Markus Aspenmeier has a lot more mass, but this is not spatial superposition. This is just a harmonic oscillator, and he manages to cool a silicea bead, which is quite big, to quantum scales. because it's very difficult, as you can imagine, to put a superposition, and the main thing is the temperature. So things are when they're solids, they're very difficult to cool down. So Marcus Arndt cools down his molecules to millikelvin scales, but cooling down larger systems is the biggest hurdle. So there's people all over the world doing experiments. There's also obviously experiments in UCL, and there's diamonds, mirrors, rods, membranes. Also in Southampton, my colleague Henrik Ulbrich has done some really beautiful experiments. He has some beautiful experiments in Southampton, but also with the group in, I think it's in Copenhagen, I don't remember where he is. They took two little beads and they tested gravity at those scales. Nothing quantum, but it's the smallest sort of particle that people have been able to measure gravity. So really, really impressive experiments. So like I was saying, I like the idea of Roger that gravity produces the collapse. Actually, the idea came two years before from Lajos Diossi, but Roger arrived to the same point by completely different arguments, and also completely independently. He didn't know about Diossi's work two years after. Diossi came up with this idea from purely classical considerations, and Roger sort of arrived there by thinking about the effects of relativity on the particles. So it's really beautiful to see the deductions are completely different, but they arrived at the same place. And well, yeah, I think it's a good idea, because a big difference between the microscopic world and the macroscopic world is mass. So I felt that it did make quite good sense to think that gravity is the culprit. So now what I want to do is go into more detail about talking about what happens with spatial superpositions and the equivalence principle. So if you remember, the equivalence principle tells us that if we are, let's say, for example, on a spaceship and we're accelerated with uniform acceleration g, we cannot distinguish that from being in the presence of a gravitational field with that same acceleration. And a special thing about gravity is that if you're in a frame that is free-falling with the system, you can sort of transform gravity away. So that is something that you cannot do with other forces. And that has also made some people, perhaps like Jonathan, argue that gravity is a different type of force, and therefore maybe we don't need to quantize it, no? So before we go into more details, I want to make a distinction, because there's two different situations that cause a lot of confusion. And one we say is related to the passive mass of the atoms in the superposition, and the other one is about the active mass. So what I mean by that is that if you look at the gravitational field of the Earth, I think this is running out of battery. The Earth is acting as the active mass on particles that are falling in the field with passive mass in that case. And then we want to look at the little system, like the bead or something like this, as being the passive mass in the active mass of the gravitational field of the Earth, and discuss what happens with the equivalence principle and the superposition principle in that case. And well, what Roger, I'm going to go into detail of that, but what Roger predicted is that in this case, quantum mechanics and general relativity are compatible. And now there is an experiment that is very new that has verified Roger's predictions. But what becomes more interesting is the case where you have active mass. So there is no Earth. Just think about the particles, maybe there's nothing else but the particle itself in superposition with itself. And then the particle is feeling like the active mass of its own, let's say, because it's in a superposition. And what Roger claimed is that this was an unstable situation and that this would enter in conflict with the equivalence principle, and therefore there had to be a collapse. So that was the arguments of Roger. So how Roger thought about first the passive situation is that this is a drawing from his book.
Sorry, in the previous slide, we're imagining those on the right. Those are the same part.
Yes.
Right.
It's just that that's kind of difficult to draw. I don't know.
Yeah.
Maybe you can suggest some drawing ways, but I'm always struggling with how do I draw a superposition? Yeah. Yes. So in both cases, there is a superposition, only that in one, the gravitational field is due to the Earth, so an external body, whereas in this is just self-gravity. So, okay, so Roger thought about the following thing. So we have an atom in the lab, and from the perspective of the lab, the atom is falling. And then you can describe the state of that atom with a wave function. So now what he did is that he thought about what happens if we now get on the reference frame falling with the atom. So that's something that we never do in quantum theory. In quantum theory, we describe physics and experiments and so on, always just from like, I don't know, the lab frame or things like that, because since clocks tick at the same rate and we have Galilean transformations, it's kind of trivial to do this transformation. So we just don't you do them very often. However, if you jump to relativity, that's what the whole thing about relativity is always talking about how physics looks like from different reference frames and so on. I mean, it's not that you don't do it in quantum theory, it's just less common. But then Roger, coming from a relativistic background, thought, okay, now I want to describe this situation from what he called the Einsteinian frame, because it's free falling with the particle. And then he says, well, if we expect quantum mechanics and general relativity to be compatible, then we would require that the quantum state, as explained from the Newtonian frame, described on the Einsteinian frame, should be the same. Otherwise, we're in trouble. Okay, but in quantum mechanics, states are equivalent up to a phase, so they could differ by a phase. And Roger calculated the phase, and the phase has a special behavior, which is that it goes with the cube of time, and that is kind of very sort of, in a way, unusual. Not so much, it has appeared in other cases with magnetic fields and so on, but it is a rather unusual dependence on time. So he did this in the 80s. So, but it's a global phase, so global phases we cannot measure in the lab. But Ron Feldman is an experimentalist in, oh gosh, I think he's in Haifa, but I might getting the wrong place. He had a really nice idea, which is to build an interferometer in which, in one of the branches of the interferometer, he keeps the particle in the lab frame. So basically, he just has the particle there levitating. Perfect, thank you. And then in the other branch of the interferometer, he gives it a kick, and then he lets the particle in free fall, and then he does interference and measures the phase. So this is how it looks like, and he has some kind of chip and so on. It's a really difficult experiment to do, and like a very delicate experiment. But the good news is that he measured the T-cube phase. These are his experimental results. And he invited me and Roger to join the paper and analyzing the results and so on. It's like I'm having trouble with this microphone. It was a bit of a mess, I must say, because he invited three groups of theorists, and we all had different points of view. So I think he said, okay, I never do this again. And we would spend just the whole time. I think it took longer to get us to agree on a version of the paper than he took doing the experiments. No, I'm just joking, but it was really tricky. But anyway, this is on the archive and is being refereed at the time. Okay, but so then those results show is that under the passive situation, under passive gravity, quantum superpositions are in, let's say, compatible. The superposition principle is compatible with the equivalence principle, and in that way, you can describe quantum mechanics and general relativity. In that case, in principle, you could in a consistent way. But what Roger has been arguing for a long time is that this is no longer the case if you look at the active case. And then he came up with this formula, which is the gravitational self-energy of the difference in the superposition, to show what is sort of the... He argued that there is an uncertainty in the energy of the system of gravitational origin that makes the state collapse. So how he thought about it, and this is also how Diossi thought about it, let's not forget, no, Diossi, because usually he gets a little bit more ignored, is that they thought, okay, I have a mass, and now I take a copy of the mass. This is where I already disagree with both of them, okay? Yeah, but what they did is the inspiration of what I'm doing now. But there I already disagree. But anyway, and then you separate them, and then you calculate the energy that you need in order to do the separation like a distance b. That is what this formula is. And then Roger used a energy uncertainty principle to get a time scale based on this gravitational self-energy where the system would collapse. Now, there is a problem here, unfortunately, which is this energy uncertainty principle is only valid under unitary transformation. Okay, so if you have unitary transformation, this holds. Oops. But, well, if you're saying that the state is going to decay and that's going to collapse, it's no longer unitary evolution, and this doesn't hold. So although I think what Roger did here is interesting and gives you, it tells you that there is a time scale, is not precisely right, and I don't think this is the right way to calculate it, and this is something also that I'm trying to refine and come up with a first principle derivation of the time scale where you would expect gravity to have these effects. So how well I got started with this because Roger was telling me about these experiments, and he was sort of complaining that it's been so many years and still people haven't been able to show that gravity collapses the wave function. And I asked him what's happening, why, and he said, well, the biggest problem is temperature, because solids are so difficult to cool down. So then I came up with a bad idea, but I mean, sometimes you have to come up with bad ideas and then lead to a good one. And well, I was curious to see what could you do with a Bose-Einstein condensate. Why? Because a Bose-Einstein condensate, you can cool down to 0.5 nanokelvin. So these are so many orders of magnitude colder than the other experiments. And I was wondering, well, if heat is a problem, could we do something here? So a Bose-Einstein condensates are atoms, and atoms are behave like bosons, that you cool down to the ground state of a harmonic oscillator. But because they're bosons, you can cool many to the ground state. So typical experiments would have 10 to the 5, 10 to the 6 atoms of rubidium. And then they can be in the same quantum state, but not quite. You cannot reach zero temperature because atoms always interact and they collide. And then these create excitations on the bulk of the BEC that are called quasi-particles or phonons or something like this. And they are a relativistic quantum field without mass, a massless relativistic quantum field. So I thought, well, why not explore that? So the nice thing is that I got to write a paper with Roger. And that was quite an exciting thing for me, as you can imagine. But in a Bose-Einstein condensate, you would have to prepare what's known as a Noon state. N atoms at the left and nothing at the right in superposition with 0 at the left and N at the right. And these states cannot be produced in the lab because they're incredibly fragile. So when you lose one atom, then the whole thing collapses. And what you want is that you want to hold this superposition long enough so that gravity acts. But the problem is that the scales in which gravity acts are very long. And the scales that people can have systems in a coherent superposition are very short in comparison. So that is like the experimental challenge, is to get the masses large enough and the decoherence controllable, such that you can assure that gravity is collapsing the wave function, not some fluctuations in your lasers or some external molecules and so on. So, but we studied this very seriously with my postdoc then, Richard Howell, that I don't know if you're aware, but there's like a big controversy now with the new work that he's done. But well, I can tell you about that later on. But there's like now a lot, not related to my work, it's stuff that he's done afterwards. Anyway, so we studied the coherence and how, what are the probabilities of having these losses. So we studied like 3-body losses and things like that that are the most common in a BEC. And what we found, but these numbers, the paper has been actually quite cited, because the numbers that we find here are useful for everybody working in the field. So what we found is that you would need around 4 times 10 to the 9 atoms to see the gravitational effects, if you could hold that coherently for around 2 seconds. So you can see how far away this is from what people are doing in the lab. Because Marcus Arndt has 2,000 atoms. Okay, if you want 20,000 atoms in a superposition, but we need 4 times 10 to the 9. This is many orders of magnitude away. Yet there are many groups that are currently trying to do this using like all the kinds of systems I've mentioned before, but even more, there's a proposal by Sugato Bose of doing superpositions, having 2 superpositions and having like the 2 branches of the superposition interact exclusively by gravity, and showing that gravity is quantum by showing that this is entangled, which is an incredibly challenging experiment. But we're going to come up with an experiment, by the way, using the Hong effect, but multi-particle, which I love. This is like such a beautiful, it's so simple, yet it's so interesting. So we're using, and I'm going to tell you a little bit about that, like a multi-particle version of it to test the effects of gravity in the quantum superpositions. And that is how we try to go around. So you see, this is what I meant. Like, this was a bit of a bad idea, because this is very far from the experiment, but also for the other systems. But this idea, this came up, give me the starting point of things that now I think are much more realistic. So let me continue telling you let's say, the story or the saga in this field, is that Roger just came up with this formula, the gravitational self-energy of the difference, but Diossi took a step forward. So what Diossi did is that he derived a microscopic model saying how things behave. And what he did is that he came up with this stochastic model known as the Diossi-Penrose model. But this model doesn't conserve energy, which is something that Roger doesn't like at all. I agree with him that this is not very desirable. But even more than that is that it predicts a spurious radiation, and people have done experiments to try to see if this radiation is observed. And this is the paper that came out recently, including here Diossi, in which they did not observe the radiation. So it's not completely like falsified, because there's still some parameter scales in which it could happen. But this is not just for gravitational induced collapse. This is in general for collapse models. This whole experiment has been so far, thank you, not very good news for the collapse models, because of this radiation not being observed. So in the newspapers, you could see after the paper was published, headlines like Angelo Bassi proved Nobel Prize winner Roger Penrose wrong, or something like that. And of course, Roger didn't like this because he insisted I don't agree that there should be a model in which there's no energy conservation. So it's not my model, it's Diossis. Diossis was kind enough to include and give credit to Roger for the idea as well of the gravitational self-energy of the difference. And that is when I decided to come in, because I felt, okay, well, maybe, I can try to do something there and see what happens. So this is how I see myself saying, okay, I have a purpose. Let's see if I can do something better. And that has been me for the last 3 years, fighting the monster. It's a simple model, but it's been very difficult for me conceptually. It's not true that it's alone. I'll show you my team in a moment. And 2 years ago, we were about to publish, and of course, we saw a special case that didn't make sense. Poof, back into the blackboard from start and again. We're now coming to conclusion, I hope. But what we did is that now we have a model which is energy conserving. It recovers a version of the gravitational self-energy of the difference, but it has something actually quite special in it. So the other thing that's nice is that we can now extend it not just to 2 particles, but to many particles. And this was important in order to try to come up with a different experimental proposal. So I was telling you that a problem with the BEC is that it's not a solid, it's a quantum gas or a quantum fluid, and you can easily lose atoms out of the condensate. But okay, you have to be careful with that. But there are other things that can happen, and this we use as an advantage, is that the atoms can tunnel from one well into the other. And this means that while solids, you can only have the lump in a superposition of left and right. Here you can have like a whole family of states. For example, imagine having n here, 0 there, n minus 1, 1, n minus 2, 2, blah, blah, blah. These are called generalized two-mode squeeze states. And people have already done states like that in the lab. At least the challenge with us is way lower than the challenge with solids. So our paper is going to come with a proposal to test the effects in a multi-particle home type effect using a Bose-Einstein condensate. So this is my team. This is my PhD students. Melanie worked in the lab with Bose-Einstein condensates, but she decided she likes more to do numerical work. So she's helping us with the simulations of the experiment. Hector has now graduated, and he's a postdoc, and he has a background similar to mine. Kia is a mathematician, so helping us with algebras, and Abdul is a philosopher. So we're going from the lab into the philosophy with my team, and I'm super excited about that. Okay, I jump all of this. No, nothing about this. I always have so much stuff, and I just talk whatever time gives me. But I just want to finish saying that we raised $5 million to do the experiment. And the experiment is already kind of underway by Philippe Boyer in Amsterdam with Chris Westbrook. And we're hiring experimentalists to do this. And if you want to hear more, a little advertisement, I have a number of videos. That's why you say I'm all over the place nowadays. But I go into other things and details of this. Thank you.
Okay, so there's time for some questions. Anybody? Peter?
Yeah, when you talked about the active and the passive, first thing, in the passive, what kind of dimensions are we talking about the superposition? Because it's something that kind of seems to be.
Yeah, that's true. That's true. I didn't say so. In the experiment that Ron Follman has, the superposition of us one atom.
Okay, but when you do your mathematical description, you're having them at 2 different positions. So the superposition is in space.
It's in space. So that's like the size of the interferometer, right? You mean the distance between the superposition?
Yeah,
How big it is?
yeah.
Oh, I think it's like, now, I don't remember if it's
But it's atomic size.
It's very micrometers, I think.
Okay. No, because when you talk then about the active,
Yes.
that you got the Earth and you got your experiment, and you seem to separate both together. But isn't there a case to think about what happens with the passive within an active?
Yes.
Because
Yes, but you want to.
sorry,
No,
the
go.
passive is so close together that maybe the gravitational interaction, let's call it, isn't that negligible compared to the gravitational field
Yes.
of the Earth.
From one atom, it's super negligible. I think the time at which you expect to have the effects is like 10 to the... We just did that calculation now, like 10 to the 20 seconds. The time in which it would have effects is tiny. So in the passive experiment, you can completely neglect the active effects.
Okay. Even though but you could have a situation where, for instance, I mean, in space,
Yeah.
where you could have a small enough active
Yeah.
that is comparable to the passive.
Yeah, well, the thing is that the active scales like the mass squared. So if you have a tiny mass, the distance really doesn't matter much. The mass is much more important in the numbers.
Yeah.
So even if you have a very small distance, it will be overtaken by the mass. So you really need to go, if you have a very small system like an atom, it's not going to work to see the active case. You really need to go to higher mass. And that's what we're proposing, but not in a lump, because the lump is super difficult, but in this multi-particle Hom effect, multi-particle interferometer. And in that case, we also need something like 10 to the 7 particles. So super challenging experiment, but easier than all the others, I think. Yes?
And with that multi-particle BC setup, so you may already have answered this question in what you said to Peter, and I just missed it, but what's the time scale in which you expect to go out of superposition, as by comparison with the solid case?
It's the same time scales.
It's the same time scale.
Yeah,
Just
so
the effect time scale.
it's well, the thing is that the experimentalists cannot hold coherent states for very long. I mean, milliseconds and so on. So we need to see how much mass do we need to put in so that we don't go over I mean, Philippe Boyer, who's very intrepid, he did experiments with atom interferometers in free fall on a plane. And he flew the plane in down, not only did the experiment, but he was piloting the plane. That is the experimentalist that I found to do the experiment. I thought he has the right sort of mind frame. He's going to do the experiment, and he thinks he could push it up to a second, but that's already, well, that's what he says, but that would be very...
That's way beyond the kind of timescales that have typically been spoken about in.
Yeah, but we're not.
case of
I
the
mean,
superposition of masses.
but we're not. I mean, we're looking at numbers below because I mean, it's a trade-off. If you want to have something lasting longer, you need less mass.
Yeah.
But if you cannot get it that long, then you need to put in more mass. So we have to find
Yeah,
the
that's
sweet.
precisely why I asked whether the BEC setup made a difference.
Yeah. So we have to find that sweet spot where hopefully it will work.
That's a fantastic idea and very, very good luck. How can I just say, the guy who actually piloted the plane himself as well as doing, I think that is really taking multitasking a bit too far.
A bit too far.
I think you do need two guys.
Let's have one more quick questions from the back.
Sorry.
So also in the active and passive gravity situation, you talked about positive active that was like the same particle interacting with each other.
Yeah.
You talked about it was kind of a problem for gravity and that people collapse things. That's not the same thing happens. For example, if you have a photon and if it's like in two different positions, it interacts electrically, or
It is the same thing.
but is it not like solved in that case? Do people do not understand the electric force?
Yes, but I mean, that is not the reason why we see the transition from the classical world into the quantum world. It's not the electric field, and I tell you why. Because then we would see things with charge, classical, but things that don't have charge would be in superposition, and we don't see that, right? So if it's the mass, so this is why this is very beautiful, because if it's the mass, anything that has mass, you cannot see in superposition. But things that don't have mass, photons, you can, satellites. Yeah, thank you.
Thank you very much.
Thanks.